Module 11 is on chemical kinetics. Now, so far this year, we've spent time looking at whether a reaction will happen spontaneously. We've spent time looking at how far a reaction will go to completion or whether an equilibrium is set up. Another important factor to consider is the rate of reaction, and that just basically means how quickly does it proceed. Rusting is one type of reaction that occurs very, very slowly over a matter of months or even years. Things are going to rust. Fireworks, on the other hand, are a reaction that happens very, very quickly in a matter of, just a fraction of a second. A firework can explode. And so there you've got examples of a reaction rate that's exceedingly slow to a reaction that's very, very, very quick. And of course, you're going to have everything in between. Now, if you've taken physics already, you're probably already familiar with rates and the rate at which things change. If you think about velocity, velocity is the rate at which displacement changes because it's a change in displacement over a change in time. If you think about acceleration, that's a rate of change of velocity, the change in velocity over the change in time. Well, this also is a rate change. It's the rate of how quickly the concentration of, and you can think of it either in terms of the concentration of the products or the concentration of the reactants, how quickly those concentration changes over a period of time. So obviously, when you think about a reaction, the concentration of the products is going to increase, whereas the concentration of the reactants is going to be decreasing. So if I have this just generic reaction, the rate for that equation is going to be some reaction constant, and this reaction constant is determined experimentally for each particular reaction. That's the only way you're able to determine these constants is to run experiments and to see what they are. Then you've got the concentration of each one of the reactants, and it is raised to a particular power. Now, what I want you to notice is that the powers that I used to raise these two are X and Y. I did not use A and B. The stoichiometric coefficients are used to raise the concentrations to powers in other types of calculations that we've done this year. But for a rate equation, it is not the same thing. You can't use the stoichiometric coefficients and just pop them in here. They may be the same, but they may not. Actually, later in the module, we'll be finding out that there is one very specific type of reaction where you can assume that they're the same as the stoichiometric coefficients. But just in general, your assumption should be that the stoichiometric coefficients are not the same as the powers that these guys are raised to. When we're talking about a rate, since we're talking about concentration, which is most often expressed in molarity, the units for rate are going to be molarity per second or molarity per minute, molarity per hour, whichever type of unit we're talking about. So it's going to be molarity over some sort of time unit. Most of this is stuff that, in this first section at least, is stuff that you should have covered in your first year class. And so the type of example problem that he gives you and that you're going to be doing today for your homework, these are exactly the same kind of sample problems or the same kind of problems that you worked in your first year course. So this should be review. And then we'll move on from it in the next section. So we'll go ahead and go through this. We're going to be looking at example 11.1 on page 332. We have this equation, and it says that a chemist is going to study the instantaneous rate of the following reaction, and then this is the data that he gets. Why do we say that it's an instantaneous rate? Well, if you look at the rate equation, you can see that the rate directly depends on the concentrations of the reactants. Well, once the reaction starts, what happens to the concentration of the reactants? It immediately goes down. And so the numbers that I put in here are only going to be valid for a flash in time, for a very small snapshot of the entire picture of this whole reaction. Okay, it's like one frame in a movie, basically, because as soon as you've got part of these reactants reacting to form products, the concentrations are no longer the same. Okay, so that's why this column is titled an instantaneous rate. And again, that's something that we're going to hit more in the next several days. But that's why it's instantaneous. It's just for one specific moment in time, because as the reaction continues to happen, these concentrations are going to change. All right, so the scientist ran 3 trials, and these were the initial concentrations of the reactants that he used, and this was the rate that he measured when the reaction started, okay? So what we want to find out is what the rate equation for this reaction looks like. So what we're trying to find is what the rate equation looks like, right, for this rate equation looks like for this particular reaction. So there are 3 things we need to find. First of all, we need to find out what these exponents are up here, and we're going to need to find out what this rate constant is. But with the information that we have here, all of that is very possible. Okay, what I want to do is I want to compare 2 trials at a time. And when I look for which trials I'm going to compare, I want to see that one reactant's concentration is held the same and the other one is changing, because that's the only way I'm going to be able to tell whether or how the rate is dependent on that particular reactant. So if I look between trial 1 and trial 2, I can see that the concentration of the hydrogen started out the same in both of those, but the concentration of the nitrogen monoxide was doubled. Okay, so for trial 1 going to trial 2, the concentration of the NO was doubled. And what happened to the rate? If you can't look at that and see it in your head, all you need to do is pull out your calculator and divide. So take this 1.134 times 10 to the minus 2 divided by 2.835 times 10 to the minus 3. And if you do that, you'll see that what happened is that the rate actually quadrupled during that period of time. So the rate, instead of writing quadrupled, I'm going to say the rate went up by a factor of 4. Okay? So what I have to ask myself is, if the rate, or if the concentration was doubled, what do I have to do to the 2 to get 4 out of it? Because remember, we're looking for an exponent, and so if this doubled, that's where that 2 came from. 2 to what power is going to give me 4? Well, hopefully you can look at that and say, well, that's pretty simple. I've got to take that to the 2nd power. I've got to square it. So what that tells me then is that in the rate equation, which is going to be this, the rate is going to be the rate constant times the concentration of nitrogen monoxide raised to some power times the concentration of the hydrogen raised to another power. What that tells me is that since I doubled the rate, or double the concentration of nitrogen monoxide, and I quadruple the rate, that tells me that this number right here is a 2. Okay, now let's look at another trial and see if we can find one where the nitrogen monoxide is held constant, but the hydrogen changes. Well, that's going to be the same between trials 2 and 3. Here you can see that this one stays the same, but now this one is doubling. So from trial 2 to trial 3, concentration of H2 doubles. What happens to the rate? Well, this one's probably a little easier to see just by looking at it, but here you can see that the rate is also going to double. So if the concentration doubles, what power do I raise that to get a 2? Well, it's going to be a 1, okay? And so that tells me is that this y here is going to be a 1, but of course we don't normally write to the 1st power. Normally we just leave it that way. Although we don't see it in this particular example problem, it is possible that a reactant has absolutely no effect on the rate. You could double it, you could triple it, and it doesn't make any difference in the rate. So be aware that that can happen also. And so if it happens that the rate doesn't change, then what power are you going to raise that to? Well, you're going to raise that to the 0 power, because anything to the 0 power is what? It's 1, if you remember that from algebra. Okay, so if you find that you have a trial where the rate doesn't change even though you've doubled the concentration, that means that exponent then is going to be a 0, because it doesn't have any effect on the rate. Okay, so now I have my rate equation. So I've got that part, but how am I going to find K? Because I still have an unknown left here. You can use the data from any of these trials to figure out what K is. You just can't mix them up. You can pick any one that you want, and it doesn't make a bit of difference. Okay, so if I take, let's say that I just take the first trial, and so for the rate, I'm going to plug in the rate that they got, which is 2.835 times 10 to the minus 3, and the constant, or the units are molarity per second, equals K times concentration of NO, which was 0.30 molar, and that's squared, times the concentration of the hydrogen, which was 0.35 molar. Okay, so when I solve that, I'm going to end up with a molarity cubed on this side, and then I'm going to divide both sides by that. And so what I'm going to end up with, the number is, I think it's, 0.090, and it's going to be, this molarity is going to cancel out with one of the molarity cubes on the bottom, so I'm going to have per molarity cube, or molarity squared per second. And that gives me what the rate constant is, okay? So now I can write the entire rate equation, putting K in there for it. And so that's going to give me rate equals 0.090 meters squared second is K times the concentration of NO squared times the concentration of H2. So this right here is my final rate equation. All right. Now, one thing that, if you're following my lesson plans, that you won't see for another day or two until you finish the lab, because I'm having you work the problems before I have you do the lab experiment, is that this here, these exponents are actually called reaction orders. And so this is the rate constant, which we can find for each reaction and is determined experimentally. But the numbers, these exponents that these guys are raised to, are called the orders of reaction. So the NO, when we found that it has this 2 up here, we say that the rate is second order with respect to NO. And we say that the rate is first order with respect to hydrogen, okay? So the rate order of 1 for the hydrogen, rate order of 2 for the NO. Then I can also have an overall order for the entire reaction, and all I have to do is add those together. So my orders are first order with respect to hydrogen. It is second order with respect to NO, and it's third order overall. Because all I have to do is add the 1 plus the 2, and that gives me the 3 for down here. Okay, so that terminology, again, you won't see that until the explanation after the lab, but I went ahead and was going to cover it now because it actually is part of this section. Okay, so hopefully going through that reminds you of some things that you did in your first year course, and then so the next time that we come back, we'll be able to learn something new.